1.08 are primary trigonometric ratios or primary trig ratios. Here we go with fresh stuff for grade 10. When working with a right angle triangle, it's helpful to name the sides. We're used to saying A, B, and C, but those names can also be dependent, the ones that we're specifically looking at, with which angle, which corner we're looking at. So here's the corner we're going to look at, and we're going to name those sides the hypotenuse, the opposite side from the corner we're looking at, and the adjacent. That's just fancy for next to. So the longest side of each right angle triangle, side C, is our hypotenuse. It's easy to see because it's across the triangle from the 90-degree corner or the right angle. So across there, there's our hypotenuse. The side opposite, or the other side, on the other side of the triangle from the angle we're looking at, is our opposite side. And then the side that goes from the angle we're looking at to the 90 degrees is our adjacent side. Cool. So we've labeled some triangles. All right, let's use that to label those 4 triangles. Okay, so the hypotenuse, let's look, hypotenuse across the triangle from the 90. Across the triangle from the 90. Across the triangle from the 90. There's our hypotenuse for all 3 sides. I'm going to put an H. Okay, our opposite is across the triangle from the 30 degrees. So across the triangle from the 30 degree, across the triangle from the 30 degree, across the triangle from the 30 degree. Okay, so there's our opposite side. And then our adjacent goes from the 30 to the 90. From the 30 to the 90, from the 30 to the 90. Now you notice all 4 of these triangles are different sizes, but they all have a 30-degree corner, a 90-degree corner, which means that the third angle is the same. They're all similar, but they're different sizes. So we're going to use a ruler to measure all 3 sides of each triangle, triangle A, B, C, and D. Now, for us, I have actually measured it ahead of time and wrote it down here on the side so that we could have it. So, if I go to about 2 decimal places, triangle A is about 2.92.
Stevens, could you call 224 and come to the office, please, Mr. Stevens?
This is the second time. I'm going to continue. If we go triangle B, it's 2.78. Triangle C, 4.34. Triangle D, 6.20. Our opposite side, if I fill them in, again, I measured ahead of time. And our adjacent side. Now, if I take the ratio and I divide the opposite side of each triangle by the hypotenuse of that same length on that same triangle, I get some numbers. And I've already calculated some of them. So 0.496, and it goes on. 0.496, so let's go 2 decimal places, 0.50. If I do that again, 0.50. 0.50. 0.50. So look at that. If we actually take specifically and use our calculator, and that's 30 degrees, and if I take sine, so these random buttons on the calculator, see that sin? If I say sin of 30 degrees, that corner that we are using, 0.50. So sine of 30 degrees actually equals 0.50. I want you to do the rest of these. Can't remember how well they work out, but if I use some more of these, cosine of 30 degrees, 0.866. All of these should be close to 0.866. And if I take this third button on our calculator, tangent, or tan of 30 degrees, 0.577. All of these should be fairly close. And if they aren't, it's because our measuring tool or the person measuring, which means I didn't actually do a good job. But if we could zoom in and I could get the exact measurements out of these Phaeda's pictures and get the exact measurements to lots of decimal places, we'd see that these would be closer and closer to being absolutely correct. Whoa, interesting thought. Okay, turn the page. So, you notice that each column, the ratio is the same or equal. This is because we use the same angle or the same corner or the same vertex in each triangle. That means for any right angle triangle with an angle of 30 degrees, all those ratios on the other page would be correct. Now this is good for any angle, not just 30, especially in a right angle triangle. So each ratio can be given a special name. So the first one that we did was opposite over hypotenuse. And so that is sine of that angle is the length of the opposite divided by the length of the hypotenuse. Even if it's a small triangle, a big triangle, it's always going to be the same number, which is equal to sine opposite over hypotenuse. Cosine is going to be the length of the adjacent side divided by the length of the hypotenuse. That ratio is going to be equal to cosine of that angle from the corner we are looking. And tangent will be the length of the opposite side divided by the length of the adjacent side. So the way that we remember this is a little thing. So, S-O-H, so, C-A-H, ca, T-O-A, toa, SOHCAHTOA, so, ca, toa. That's our primary trig ratio, SOHCAHTOA. Say it, SOHCAHTOA, 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 SOHCAHTOA. All right. Okay. So, our examples. Find the three primary trig ratios for the following angles. Sine of A. Well, if I'm looking at A, corner A, then again, here's my 90. So there is my hypotenuse. On the other side from this angle I'm looking at is my opposite. And then from my angle, the corner I'm looking at, specifically A, to the 90 is my adjacent. So sine of A from corner A is going to be opposite over hypotenuse. So sine is opposite over hypotenuse. So specifically, it's going to be 5 over 13. cosine, so ka, A over H. So it's going to be adjacent over hypotenuse. Tangent, tan, SOHCAHTOA, not toe, but toa. Tan, we're going to use opposite over adjacent, so 5 over 12. Okay, so I could calculate that and see what they actually are, and then figure out what the actual angle is, and I would have the same angle for all three. If I do it now without color coordinating, looking at vertex B, or corner B, I think there's my 90, so there's my hypotenuse. On the other side of the triangle from the corner I'm looking at is my opposite, and from the corner I'm looking at to the 90 is the adjacent. So sine, so opposite over hypotenuse. Ka, so cosine is adjacent over hypotenuse. Toa, tan is opposite over adjacent. All right, flip the page and let's see how we actually use this to solve things.